Well, hello and welcome again to our journey into number theory. And we had a look at Bertrand's postulate in the previous section, and now I want to say a few little words about primes in arithmetic progressions. So we saw earlier that we know that there are infinitely many primes, and we saw earlier that the primes naturally split into those which are congruent to 1 mod 4 and those that are congruent to minus 1 mod 4. For example, we saw that the 1 mod 4 primes are the sums of two squares. And we want to, in this bit, I'm just going to prove that there are infinitely many. We know there are infinitely many primes, but in fact there are infinitely many primes congruent to 1 mod 4 and infinitely many primes congruent to 3 mod 4 or minus 1 mod 4. And so that's our next little theorem here. Now these two results are special cases of a much more general result called Dirichlet's theorem, and we'll in fact spend quite a long time going through and proving this general result, that if you take a general arithmetic sequence in which the first two terms are relatively prime, then that always contains infinitely many primes. These proofs we're going to do here are fairly ad hoc proofs. They don't generalize nicely. We need something better, which is character theory, which we'll get to in a later chapter. So these proofs and ones like them are just, they're all quite individual and have got their own little tricks in them. So I'm going to model this one on our proof that there were infinitely many primes. And so we're going to do it by contradiction. So once again, for a contradiction, we suppose we have all of the primes, q1 up to qn, that are congruent to minus 1 mod 4. We have all of the minus 1 mod 4 primes. There they are in this set S, and there are no more. And just as in the Euclid proof, you multiply them together and add 1, here I'm going to multiply them together, multiply by 4 and subtract 1. The point being then that I have another number here which is congruent to minus 1 mod 4. Now n is odd, so the only factors of n have to be odd numbers. If n is prime, then we've got a contradiction immediately, because n is congruent to minus 1 mod 4 and n clearly doesn't belong to our set S of all such primes. So otherwise, if n must have prime factors. Moreover, because this number here, if you divide that by any of these, you get a remainder. So if n has prime factors, then they have to all be congruent to 1 mod 4. You can't have any congruent to minus 1 mod 4, because then that would also give you a contradiction, because they would not belong to our set S. But the trouble is then, when you multiply numbers together that are congruent to 1 mod 4, then the product is congruent to 1 mod 4. And the trouble is, when you do that, you get a number congruent to 1 mod 4, but of course the product of all those is going to be my n, and n is minus 1 mod 4. So that's a contradiction, and so no such set exists. So the proof is fairly similar to that based on Euclid's idea. Now the same kind of argument unfortunately does not work with the 1 mod 4 primes, even though there are infinitely many of them. And so I need a different proof to prove there are infinitely many primes congruent to 1 mod 4. And it's quite different in flavour. So this one, we're actually this is a constructive proof. So we take any n bigger than 1, and I'm going to show that there exists a prime p, which is 1 mod 4, which is bigger than n. So you take any n bigger than 1, we show how to construct a 1 mod 4 prime that's bigger than n. Since n is arbitrary, this will show that there are infinitely many such primes. And I'm going to let m be n factorial squared plus 1. And so m then is going to be an odd number, because n factorial will be even, and when you square it you get even. So this is odd and it's bigger than 1. So let p be the smallest prime factor of m. So So we take this number and we take p to be the smallest prime factor of n. Clearly it has to be bigger than n, and also it's clear that none of the numbers 2, 3 up to n divides m, because each of these numbers divides n factorial squared, and there's always a remainder of 1. That means then that modulo this prime p, this thing has to be is 0 mod p, because p is a prime factor of this, and so that says n factorial squared is minus 1 mod p. Now I'm going to raise both sides of this to the power p minus 1 over 2. Raise both sides to the power p minus 1 over 2. So I'm going to get n factorial to the p minus 1 over 2, well, it's n factorial squared to the p minus 1 over 2 is just n factorial to the p minus 1, and this side we get minus 1 to the p minus 1 over 2. Now by Fermat's little theorem, this thing here of course has to be 1, and that means this has to be 1, but that means p minus 1 over 2 has to be even. And that tells us that p then is a 1 mod 4 prime. So that means for each n bigger than 1, we can find, in a constructive way, a prime p which is 1 mod 4 and which is bigger than n. And therefore we conclude there are infinitely many such primes. Now of course those proofs are all very nice and very interesting, but they don't give us any idea of how one might generalize this. Suppose we're working modulo 8, can we prove there are infinitely many primes 1 mod 8, or 3 mod 8, or 5 mod 8, or 7 mod 8, and so on. We need a much more general way of dealing with that, and that we will deal with in a later chapter when we look at this famous theorem due to Dirichlet. So, as I mentioned here, these are very special cases of Dirichlet's theorem, and it states that if you've got two numbers that are relatively prime, then this arithmetic series, which starts off with the first two numbers being relatively prime, or a and a plus b relatively prime, this contains infinitely many primes. And we'll look at this later in chapter 4. Now the next little section, I want to have a look at some of the work that was done by Chebychev, and I'm going to return to the function pi of x. And I'm going to start this section and I'll state the result, and I'll finish the proof in the next section. The proofs are going to be fairly technical, and you might care to skip that one, but I'll include it for the sake of completeness. So at the age of 14, heaven spare us, Gauss guessed that this function pi of x can be asymptotically approximated by x on log x. This is log to the base e. Well, I mean, nowadays I think most 14-year-olds have not met logarithms to the base e, but Gauss not only had met them, but he also guessed that the number of primes less or equal to x was roughly in the ballpark of x on log x. Now, what do we mean by asymptotically approximated by? Well, we mean that if I take pi of x divided by x on log x, then this goes to 1 as x goes to infinity. And this result, Gauss couldn't prove this, by the way, but this result is, of course, known as the prime number theorem, as one of the most important theorems in analytic number theory. And we will prove it a bit later on in one of the later chapters. Gauss himself, of course, could not prove it. Chebychev was able to show that it was at least roughly correct. More precisely, he proved that if pi of x was asymptotic to something times x on log x, then that c had to be 1. And he also showed that there were constants a and b, so that pi of x is bigger or equal to ax on log x and less or equal to bx on log x. we will do a similar thing, and we're going to find such constants a and b. Probably not quite as good as the ones Chebychev found, but they will at least do for the time being until we get to the prime number theorem. Now, to get to this result, we need a couple of lemmas, of technical lemmas, about the binomial coefficient. It's very interesting, I think. We saw when we looked at Bertrand's postulate this connection between the binomial coefficients, or the use of the binomial coefficients, and proving these various facts about prime numbers. So for n bigger or equal to 1, the binomial coefficient 2n on n is bigger or equal to 2 to the n, and it's less or equal to 2 to the 2n. The second result is that if you've got a prime dividing the binomial coefficient 2n choose n, then that happens for every prime between n and 2n. So every prime between n and 2n is a factor of the binomial coefficient 2n choose n. So I'll just have a quick look at the little proofs of this. So the first one, we're proving that 2 to the n is less than 2n choose n is less than 2 to the 2n. And the second one, we're proving that every prime p between n and 2n is a factor of that binomial coefficient. For example, if I take 12 choose 6, so taking n as 6, that number is 924, and the primes between 6 and 12 are 7 and 11, and both of these are in fact factors of 924. Now the proofs of this lemma is actually fairly easy. Well, firstly, of course, 2 to the 2n is, you can write as 1 plus 1 to the 2n, which you can expand out as using the binomial theorem. And of course, that's bigger than one of the terms. The middle term here is 2n choose n, so that's clearly bigger than that. On the other hand, 2n choose n is 2n factorial on n factorial squared, and I can cancel out, I can write this as n factorial on the bottom, the second n factorial cancelling with what bits on the top, and you just get 2n minus 1 up to n plus 1. And then you can simply say 2n on n is 2, 2n minus 1 on n minus 1 is bigger than 2, and so on. All of these terms are all bigger than 2. This occurs n times, so this is 2 to the n. And for the second part, well, when you write down the binomial coefficient 2n choose n, and you cancel out the n, one of the n factorials, as we did above, you get this expression here. So if you've got a prime between n and 2n, it's going to have to occur in the numerator, but it's not going to be in the denominator. And so that means every prime between, in this range, has to divide 2n choose n. So that's a little proof of the lemma. Now, the result that we're going to prove is, and this is a la Chebychev, he had slightly different, he was able to tighten up the constants a bit, but this is not too bad here. Here we're going to show that pi of x is bigger or equal to 2/3, so that's about 0.67 x on log x, but less than 1.7 x on log x. That is, that x on log x is not a bad approximation to pi of x. Chebychev was in fact able to tighten up the left-hand constant to this one here, to 0.9 rather than 0.6, and he was able to reduce this constant to 1.1. But these can be further refined. And in some sense, they're not quite so important once we've got the prime number theorem. Now, the proof of this I'm going to do in the next recording. The proof is fairly technical. I'll record it for the sake of completeness, but you might care to skip the actual technical proof. I'll leave that for you to decide.